Hello, my friends of Battery Labs. Welcome to this class, to this webinar. This webinar is on groundwater modeling of faults and fractures with Modflow6 and the Disv or Model Muse. And this webinar is really focused on developing a small grid cell size on the vicinity of the webinar of the faults or fractures. Okay, so and this can be done with the Disv. This can in Modflow6. This can be done with many features like Modflow and the structured grid and the Voronoi meshes. But in Model Muse, the Disv with the quad tree option is the one that is implemented. So actually we are going to do that. Okay, because why we do that in Model Muse? Because in Model Muse uh, it's much easier for you. Otherwise I have to do it with Python and FlowPy. Okay, if you have any if you are still here with if you are here with me, please type 2. If you have any questions, let me know. Okay, so but okay, there is okay, but if we want to model with open source software fractures and faults on its truly okay with a model that actually represents the fractures and faults, we have to work with a software that is different works. Okay, that is a software that is oriented to develop uh, that where you can actually insert the faults and fractures. Okay, okay, so far this is the software, and this software works with a measure, and the measure is kind of is laggy. Okay, it's a measure that actually that helps you. Okay, so this is the link. Okay, that helps you to do mesh. Okay, but in these meshes tutorials and examples you can do, and then you can insert the different stratigraphy and the faults and different refinements. And in this case the faults are the these are not any longer uh, layers, but these are tetraeder. Okay, so and what is okay, so this software developed by the Los Alamos National Institute or National Laboratory, something like that, but this runs in Linux, I guess. So but what we are going to do, we are going to create a session where we can open a virtual computer or that runs Linux that has the software already installed, and then we are going to work for that. Okay, if you are interested, please type 3. If you are not interested, don't type anything. Okay, this will come from this will apply for coming webinars. Okay, so if you are interested in this type of webinar, please type 3. Otherwise, don't do that. Great. Because in these cases, we are going to model the fracture. I mean, we are going to model the discontinuity. Okay, great. So let's see, let's start. Um, so let's see, women. But I warn you, there are no GUI for this software. So actually, we are going to build a model based on the input text files. Okay. So let's see. Okay, we have a reference model that I have created. Okay, so I'm going to be based on my model. Okay, but for you, just type Model Muse. We are going to create a new Modflow model. Next. Uh, we are going to work with meters and seconds that are the default values. Don't worry. Next. And here we are going to have just one layer group. Okay. One layer group that will be called aquifer. Aquifer. Great. And then here type, please press no grid, and type 1 and type 4 on the chat. Okay, 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 okay. Okay, great. No grid. Okay, so we are going to open our, we are going to create, okay, we are going to create a model. So file, import shapefile. So let's everybody please file, import shapefile. Okay, and what we are going to do is we are going to work with the basing. So we are going to we go to documents, to the webinar, to shapefile, and then here we have the basins. The basins. Okay, so here on the basins, what we have here is, okay, set value of enclosed cells, 0 formulas, that's it. Enclosed cells and 0 formulas, that's it, enclosed cells. Okay, and then we look for this object on our unused objects because it's actually unused. Okay, and this one will set up a set grid cell size of 1000, and then we can change that of color. If you are here with me, please take 5. If you are here with me, please take 5. Okay, I will do it again. Okay, I will delete this. Okay, file, import shapefile, basing. Okay, so set value of enclosed cell, 0 formulas. Okay, then we go here to the unused objects, show or hide objects, basing. Okay, and then here we choose to set the grid cell size, and as well we change that of color. Okay, great. Great, 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 great. So, okay, so we have set it up to set the grid cell size. So, and then we explode the grid. Okay, so we generate a grid, and that is a grid. Okay, this is a grid with a coarse. Okay, this is the base grid that has a coarse cell size. Okay, great. If you are here with me, please type 6. You are doing amazing. Okay, does anybody of you is from Turkey? Let me know. Great. So let's see. Well, we can do many things now. So first of all, let's see. Let's try to import the faults. Okay, so we have the faults in the AOI. Okay, so let's see. Okay, so let's say file, import shapefile. Okay, so we have two faults. So we have faults in the area of interest and then faults in the basin. So let's open the faults in the area of interest. Okay, set value of intersected cells, and zero formulas. Okay, so these are just the faults in the basin. No, this is in the area of interest. Okay, faults in the area of interest, and then we can change that of color. Okay, change that of color. And then we have another faults. So we say 5 import shapefile, and the other faults are the faults in the basin. Okay, so these are the faults in the basin. Yeah, set value of intersected cells. Okay, and these are the all the faults. Okay, why we do that? Because you are going to see that due to the how you create the mesh, okay, you are going to have, okay, so let's see that in the AOI, because actually there is a polygon, AOI polygon. No, that actually was not. Okay, there is a polygon file, import shapefile. There is a AOI polygon, set value of enclosed cells. Okay, there is an area. Okay, so you have the whole basin. Okay, so but the whole basin is actually not of your interest, because actually you want to know in great detail what happens in a specific area. So this is the area of interest. Okay, so that is why we differentiate in between all the faults and the faults that are inside there, because for the faults that are inside this area of interest, we are going to have an even smaller grid cell size. Okay, if you are here with me, please type 7. Okay, great. So this is, I just changed this of color. Yes, always nice to change that of color, because everything will be okay. That's it. So maybe another color, because actually I cannot differentiate from anything else. Green. Okay, that's it. So we have two area of interest. Okay, so but then you will tell me, okay, so far I don't see how I can make smaller grids instead of the normal way of doing a lot of columns and rows, and say, where is that? So we go to grid, and then we switch to Disv. Okay, please go to grid and switch to Disv. Everybody, go to grid and switch to Disv and type 8. Mhm. Okay, if you are just following that, and then but you get the concept, please also type 8, because actually what I want is that even that you are just following that, you get the concepts. Okay, great. So what is here? What is here is that you have the area of interest, but this cross section is just from the line alignment. Okay, so I can change this alignment, and this will mean the cross section here, for example. Okay, or I can, for example, so actually this difference from the other part where you have the cross section here and here. Okay, so this is different. Great. Bello o Motayo, where are you from, Bello? uh, Nigeria, yes, because in Castilian Spanish, bello means beautiful. So actually, this is a pretty nice name. So, great. Okay. Yeah. So let's see. Uh, Okay, so we have the okay. Wise. Interesting. Now I know. Okay, so let's see. We are okay. So we have the false, and then we have the basing. Okay, we can import the ah. What is what what is more important here is to create the grid. Okay. Wait. I'm going to mute you. Okay, great. What is important here is that I will create the grid and then I will import the no I will create the grid and then I will import the dem because I want that, otherwise I have to set up an interpolation and it will be more messy. Okay, so let's create our grid. Let's create our grid based on this. So let's see. So for the polygon, in the polygon side, we are going to set the grid cell size to 250, okay? To 250, great, and then we generate the grid again. Okay, and this is what's the normal discretization, okay? This is the normal discretization of Model Muse, okay, or Modflow, where you in order to do a discretization, you do more columns and more rows, okay? But this is needed, okay, in order to achieve, okay, this is kind of an intermediate grid, okay? So let's see, okay, so let's go to the all objects. Let's open the faults AOI. And then we are going to, and here we are going to do a quadri refinement of 4. Okay, so what does it mean, a quadri refinement of 4? So listen to me, okay, listen to me. Okay, so a level of one quadri refinement of 1, so from the whole depth you are going to have the half, so this is 1 of the from, and then from the half of the depth of the length you are going to have the half, so this is actually the level 2, so it's 1/4. Okay, the level 3 is 1/8, and the level 4 is 1/16. So this will be 1/16, so it will have 4 intermediate. Okay, and then you are going to see that it's going to split in 4 intermediate levels. Okay, while for the faults on the basing, we are only going to have 2 levels of refinement. Okay, that's it. Okay, so here for the faults in the AOI is 4, and the faults in the basing is actually 2. Okay, so okay, and in this part is good to have to set up model 2 to save your project. Okay, if you are here with me, please type. If you are here with me, please type 9. Okay, who else is here with me? Okay, now let's do the magic. So here we can just create well, we can do a smooth grid. It's also possible. Okay, and that's it. That's it. That's it. So, okay, let's see first the refinement here. Okay, so the course grid was of size 1000. Okay, and for the regional fracture, we have set up two quadrilevels. Of these two quadrilevels, okay, so it will have gone from 1000 to 500, this is one level, to 250, this is two levels. So actually the grid cell size here will be 250. Okay, if you have understood this, please type 1. However, let's go to the refinement. Okay, because on the refinement the size is actually not 1000 anymore, it's 250. Okay, and from this 250, okay, 250 is the initial grid size, it goes one level, so it's 125. Two levels is 60, 125, 62.5. Three levels, 31. Four levels, 16. Okay, so if we, okay, so this is the first level, second level, third level, fourth level, and here what we have is $16 around. Okay, if you have understood that, because this is the key here, please type 2. This is the key part of our, please type 2. Okay, great. Great. So, and that's it. Okay, that's it mostly. Okay, now you have your refinement. Besides of doing your refinement, let me tell you that just today I have launched what it will be the coming Python for the new version of this Python for water diploma in Python for water resources, that it will be a diploma from November 2024 to February 2025, without classes in Thanksgiving and without classes in at Christmas, even New Year's Eve. Okay, and this is the right diploma in Python, that if you have seen awesome stuff in Python and then you say, okay, I want the Python level to get into these new libraries, new tools. Okay, this is the diploma that will give you the level. Okay, so okay, and as I told you, we are only supported by the courses that we sell, so it will be nice to see you there. Okay, thank you. Great. So now let's import the them, because now that we have the grid, now we can import the them file, import surface grid file, and now we, from the surface grid file is on raster them. Okay, and then we apply directly to model top, set value of intersected by interpolation is the same, because actually it will be mostly intersected. Okay, if you are here with me, please type 3. Give me three more people. Yes, Lester and Paxton. Great, Wajin. Rayen. Bello. Handsome. Yes. Nice. Uh, okay, so we put model top. And then you are going to see, well, okay, now we are going to fix this. Okay, but you're going to see something like this. Okay, so it's so you have already them. Okay, so let's fix that. Okay, so let's go to data, edit datasets, data, edit datasets, required hydrology. Okay, so no, first let's go to model, let's go to layer groups, model layer groups, and then just three. Divide this in three. Okay, you can divide this in more layers, okay? But my advice is that, okay, for the purpose of the webinar, I cannot, okay, for the purpose of the webinar, I cannot give you a heavy model because it will be too too slow for everybody to run the model, to build the model, so that is why this is a lighter model. Okay, so what we have done, model, Modflow layer groups, okay, and three. That is awesome. Okay, so yeah, so that's it. Okay, so now we go to data, edit global variable, no, data, edit datasets, required, okay, data, edit datasets, required, hydrology, okay, and active, everything is active. On the cell type, we are going to case layer of 1, of 0, of 0. Okay, so the first layer will be convertible while the rest is confined. Okay, if you are here with me, please type which number were we? 4. Below, I have to, unfortunately, I have to, as I told you, this will be for the Patreon subscribers. Yeah, it's not, still, I'm kind of ashamed of doing this, but some things cost, okay, and they cost the time that I develop in researching, and also cost the need that, well, the professional needs or personal needs, so that is why it's limited to that. Okay, so I strongly recommend you that you pick everything from here. Okay, so this is the kx, yeah, kx apply, so we apply that, so the cell type is this, the I domain, well, is the kx, on the kx, so we are going to use case layer of 0 0.002, 110 to the minus 5, 10 to the minus 5. Okay, great. So this is the for the kx. If you are here with me, please type 5. Okay. Okay, so we have higher hydraulic conductivities for the upper layer. That is normal. Okay, great. Apply. Okay, ky is equal to kz, and kx divided by 10. The initial head is model top. The initial head, instead of 0, is actually model top. Okay, apply. Initial head model top. And on the aquifer bottom, it will be, instead of 0, will be 1000. Okay, so aquifer bottom is 1000. So let's have a review. Aquifer bottom 1000, Modflow initial head is model top, kx is this, and cell type is this. Okay, if you are here with me, please type 6, 6, 6, 6, 6, 6, 6. Great, 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 great. apply and close. Okay, so you have already your parameters. Okay, and on the data visualization in the vertical acceleration, we are going to put 2. Great, that is amazing. And what else? What else? Okay. So we can check. Okay, so we can move the cross section because I want to see. Okay. Okay. Yeah, there is a problem here. If you see, there are some kind of teeted like yes, that is when we have set that the surface grids the surface grid the depth as a surface grid file, it has applied for the intersected and interpolated, but we haven't defined the interpolation method. So for that, we have to go to data, edit data sets. In model top, we set up a fitted surface and apply. Okay, so we went to model top and then just put fitted surface and press apply, and that will be okay. If you are here with me, please type 7. Okay, great. Give me 3 more. Hello, where are you? Great, Alisa. Okay. I will explain. The surface grid file has with a resolution of 30 meters. Okay, that comes the surface grid file. Okay, however, the minimum cell size is 15. So for some cells, you don't have an intersected point for the surface grid file. You don't have that. Okay, and for that you have to interpolate in between the points of the surface grid of the grid files in order to define the elevation of your point Okay, is that understood, Lester? Okay, great. Great. Okay, that's it. So let's continue with, okay. So if you want to put a background for file, okay, so we do, okay, file, import image, okay, select image, okay, and from raster we have a background photo.jpg that already comes with a Word file, okay, and this is exported from QGIS, okay, so you don't have to do that much, okay, there is a tutorial on this, okay, so this is just imported from QGIS, so just the base map, and it also exported with the Word file, so that is okay. Okay, and this is here you can impress your clients and so but it's a trick. Then we can say just for that we can define this just for the we can define just for the active area. Okay, if you are here with me, please type 8. Okay, the next steps from this tutorial are from this webinar are to set the the packaging programs, and then we have to run the model. Okay. Okay. So from the packaging programs, we are going to model, we are going to do packaging programs. Okay, when you do the Disv, actually it implements the ghost node correction. Okay, if you want to know more about the node correction, please read the documentation, because actually creates is something that relates cells in between different sizes. Okay, so we go to the recharge and the drain. So we are only going to work with these two boundary conditions, recharge and the drain. And on the solver, we are going to work with the big G stub. Okay, the drain, the well, and the recharge is on the top layer. Yeah, it's only the top layer because the layers are really thick. You can also put topography cell. I don't think that it will make any. Okay, recharge to active cell, drainage, and here linear BG stub. Okay, if you are here with me, please type 9. Okay, boundary condition plus silver. What is silver CHD, my friend? Okay, great. So let's see. Okay, so let's see. Let's import file, import shapefile, file import shapefile, and let's open the shapefile from the rivers. Okay, so we are going to import the rivers, set value of intersected cells, set value of intersected cells, one formula model top. So this will be applied to model top, set value of intersected cells and model top. Okay, and this will import the rivers. These are the rivers that I selected them again, and then I change those of color. Why not? Okay, and then here on Modflow features, I just type that this is a drain that goes from -1 to 0, that the elevation is direct, that the model, that the elevation is model top, and that the conductance is 0.01. Okay, and the discharge scaling length, okay, I have reviewed that on the documentation. I didn't understand that, but I get to know that with 0 is actually the same as it was in the beginning. Okay, so that is for this boundary condition. If you are here with me, please type 1. Any questions? Let me know. Let me know. Need 2 more people. Okay, so now I have my boundary conditions. So, okay, so let's see what I have. I have the ascertain, I have the base, I have the false, I have the the faults in the basin, I have the rivers. What I do need is the recharge. Okay, what is the recharge? Okay, so let's create a recharge value. Okay, so we are going to create an object that encloses all our, okay, all of our grid of the back paper recharge. Let's ask if the conductance of the drain will be calculated based on the K of the cell. No, 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 no. Okay, yeah. The topic of, okay, let's go back. Let's go back because the the question of Lester. Okay, you don't do nothing. I will go back only. The question of Lester is actually interesting. Okay, so this chart scaling. Okay, okay. The amount of that discharges to a drain is actually defined by the conductance of the aquifer. Okay, no, by the hydraulic conductivity of the aquifer, and the conductance is kind of a second level of restriction. Okay, that can allow you to discharge all what the aquifer has, or like it can limit as well that amount. Okay, representing some sediments or clayly material on the bottom of the drain. Okay, then in the latest version it came this discharge scaling length. That is a length, and I don't know exactly what that does mean. I mean, to tell you the truth, I haven't spent that much time in the documentation, but it's there. I mean, and then if you have time to discuss that, if you go to documentation, you have time to discuss and bring me another idea of what is on the discharge lane. This is my WhatsApp number. Okay, yeah, because I actually weren't able to do this. Okay, great. Okay, so let's go here. Let's create this. This will be recharge, as I told you. That will be on model top. Yeah, we can change that of color. And here on Modflow features, we go to recharge, and the recharge will be a value that is 150 millimeters per year, but this is in meters per second, so just type this value, 8.7 e to the minus 9. Okay, and that's it. Great. Okay, if you are here with me, please type 1 Avera Velo that asks if this has anything to do with the salinity. No, it doesn't have anything to do with the salinity. Okay, and Avera asks that the drain take water out. Yeah, in the water balance is out of the system. Okay, but the amount of water that takes out of the system is defined by two things: the K of the aquifer and the conductance. Okay, if you are here with me, please type 1. Okay, so we have recharge, we have drains, we have the discretization, we have the local discretization, we have the K, we are running on a steady state. Something else that might be missing? Any of you? Come on. No one? Okay. Save again. Okay. I will do my second check. Reverse. So we have the result size. We have the data sets for the key. No, not the X3D, but our faults. Okay, we have to file import shapefile. We have to re-import the faults of the basing. Why we have to re-import the basing? Because we are not going to set it these faults for. We are not going to use these faults for setting the grid. However, this will be from model top to aquifer bottom. Okay. Okay, but this will be in order to define the hydraulic conductivity. Okay, so because in these faults, what we are going to do, what we are going to say is that the hydraulic conductivity will be 4 times higher than the normal hydraulic conductivity of the first layer and like 80 times higher than the, how many times? Yeah, 80 times higher than the hydraulic conductivity of the second and the third layer. Okay, is file import shapefile, and this is false basic. False basing 2. Hey, wait. What happened? Okay. Once again, file import shapefile, false basing. Okay, set value of intersected cells 2 that go from model top to aquifer bottom. Okay, we re-import that. Okay, you are going to see that on black color. So and then we select these faults. Okay, we select the faults. Okay, maybe the recharge object is actually preventing you from selecting the drain fault. You just have right click, select, and hide selected object, and with that you can select the faults with ease. Okay, so this is foul basing 2. We change that of color. Okay, and here we do kx of 0.08. Okay, great. And the k set is by default is kx divided by 10. Okay. There was a. If you're here with me, please type 1. Okay. In the beginning, I wanted to do. What I wanted to do is um, I wanted to do uh, a particle tracking, okay, in order to show you that particles will arrive, will reach the fracture, and it will be discharged afterwards, okay. The problem that is that when 3D, the minimum size of the cell is 150. So actually I cannot release particles here because it will prevent my grid from running, okay, because like a modpad cannot run in cells that are less than 150. Okay, great, great. Okay, great. Save your model and run the model. I remember something. This this video will be posted. Okay, this video will be available right now for the Patreon subscriber. Okay, but they will post it in 3 weeks. Okay, so actually, yeah, you are going to see the video. Okay, but this video, okay, there are other videos that will, well, some of the videos will be released later on, some of the videos won't. Okay, but as I remember, this one will be released in 3 weeks from now, but available to the Patreon subscribers from now. Okay, so we run the model. We run the model. Okay. If it has finished for you, please type 2. If it has finished for you, please type 2. Please type 2. Type 2 if it has finished. Great, Denny. Which computer are you working with? i7, i9? Oh, I have a problem here that it hasn't made the convergence, okay? That could happen, okay? And in fact, it's most probably that when you work with this amount that you're going to find a non-convergence. I mean, 90% cases. In this case, we are not going to solve the non-convergence because we have to pick it out. Maybe we have to relax the solver. But in general sense, a discretization 0.2 is kind of acceptable in order to, in this research. Okay, do you agree with that, Lester? Okay, great. Okay, if you are here with me, please type 2. If you are here with me, please type 2. Great. So we close this. Okay. So this is the recharge, actually give this amount of liters per second on the extension, and it goes to the drain. So, and then we can open the results, the model2.bhd as a control grid. Why as a control grid? Because in the control grid, or by default, will tweak the flow. Okay, so this will tweak the flow. In FlowPy, you can do some quiver plots that actually will see the vectors. And let's go here to data visualization, to contour data, and here will be 0. Just to have more. Okay, and then we can change this of full color scheme. Okay, so let's see. Let's go to the upper part. Let's go to this part. And let's do a zoom here. And I will put just the active part. Okay, because the grid is kind of close. Okay, here we see some impact in the first layer of the drains okay, but here the difference in between the K of the faults and the K of the aquifer is just of 4 orders of, is just 4 times, so actually it's not that much in terms of hydraulic conductivity. Here we see some impact on here. Let's see in the other layer where we have that the K of the aquifer is 1 10 to the minus 5, while the K of the faults is 1 10 to the minus 3. And here we see the impact, okay? Here we see how the impact was, how the heads are affected because the faults are taking water and are conducting this water and are releasing this water later on. Okay, it will be more, for example, here we see a release part of where the fault is releasing water, and here we see a part where the fault is draining water. Okay, yeah, it will be more graphical if we can do whether a quiver plot or whether we can do a quiver plot, or whether we can do particle tracking. But in the case of particle tracking, we cannot do that because the sizes are really small. That's it. Okay, so also webinar, we have learned a lot. If you're here with me, please type 3. That will be the content of the webinar.